Okay, welcome to problem 7.65. Okay, we got a truck loading station at a post office, and a kind of weird and interesting one, I guess, too. We've got a little quarter of a circle package here. You can see it right there. It's got a radius of 1.6 meters. They mark that over here. Okay, okay. And the package is pretty small, so we can treat it as a particle. That's very thoughtful of them to let us do that. And they say that when it gets down to here, it's got a speed of 4.8 meters per second when it gets to this point there. Okay. And then they tell us that it slides to here, it slides along this little ramp area down here. When it gets to the end, comes to rest. Okay. And then we want to know first, what's the coefficient of kinetic friction on the horizontal surface? So we're going to solve that first. So what is the coefficient of horizontal friction on that surface? Okay. So I'm going to start by just conserving energy along just the bottom part of the ramp, so or just that horizontal part. So let's do energy on just the horizontal surface. Okay. So in this case, at point B, so the energy at point B should equal the energy at point C. Okay. So what that means for us is that at point B, well, we've already gone all the way down the ramp. So we should have just kinetic energy at that point. And when we've gone all the way across the ramp, we won't have any kinetic energy, but we will have used up a ton of work from a NC, from a non-conservative force, basically the friction that acts across it. So this is going to be 1/2 mv squared. That's going to be our speed at point B equals the force of friction times the distance it went across the ramp. Okay. And because it's on a horizontal ramp, this is just going to be mu mg times the distance. Okay. Well, it works out nicely. The masses divide out. I'm going to move all this stuff over toward the left side of the screen. I'm going to move it so that mu is by itself. So I'm going to have basically v squared over 2 GD is going to give me what the coefficient of friction is going to be. So it's going to be 4.8 meters per second quantity squared over 2 times 9.8 meters per second squared times 3 meters, because that's how far it goes along there. Notice the units on the bottom are meters squared per second squared, meters squared per second squared. Along the top, those are going to divide out to give me a dimensionless unit, which is exactly what I want for coefficient of friction. And I get an answer of 0.39. Okay, the second part of this problem is asking how much work is done on the package by friction as it slides down the circular arc from A to B. Well, I hadn't thought any work was done actually initially, and I thought, well, why'd they ask that? I'm like, well, that must have been some work got done as it went across. I guess there was friction on the whole track. There couldn't have been friction on one part and not the other, I guess, unless they told us. So I said, well, all right, well, let's see. Started with the very top. So I'm going to say that again, I'm going to go with the conservation of energy, that the energy at A equals the energy at B. Okay. Okay. So at the very top, it's going to have a gravitational potential energy. At the very bottom, it's going to have that kinetic energy that we had before. But if they said there's work done, I must have to include that here as well. Work done between A and B. some non-conservative work. That must be what we're solving for. Okay. So I'm going to sum that up. mgh equals 1/2 mv squared plus my non-conservative work. Tell me my friction force. Now that would be really pain to solve for if you had to solve for individually, because even if it was a constant coefficient of friction, the normal force is going to change as you go down the ramp. You know, up at the top of the ramp, it's going to be close to 0 at A, and it's going to be different. It's going to actually increase as you go down the ramp. Oh, that'd be a pain to do, even with some calculus. I guess it'd be kind of fun, but it would be a pain. But in any case, with work, we can avoid it. So that means the work done is going to be just mgh minus 1/2 mv squared. So now we just plug in all the numbers. That's just 0.12 kilograms times 9.8 meters per second squared. The height is going to be this entire radius, that 1.6 minus 1/2, 0.12 kilograms. And again, we know that speed at the bottom is 4.8 meters per second, quantity squared. And if we subtract those all out together, we should get 0.83 joules.